Imagine trying to understand a massive, intricate painting, like, say, the Mona Lisa, right?
Hmm.
Or some huge, sprawling mural. But you are only allowed to look at it through a tiny, narrow drinking straw.
Wow, yeah. You'd only see, what, a fraction of an inch at a time?
Exactly. You'd have to scan it painstakingly, millimeter by millimeter from left to right. It would just be an exhausting way to view art.
I mean, you'd completely lose the context of what you're looking at.
Right. And the real fatal flaw is by the time you finally scan your way down to the bottom right corner, your brain has completely forgotten what the top left corner even looked like.
Yeah, you have all these fragmented details, but you completely miss the big picture.
Exactly. And that exhausting, narrow view, that was basically the reality of artificial intelligence for years.
It really was. It was the ultimate, missing the forest for the trees scenario.
Mm.
And it perfectly encapsulates the core struggle of early neural networks. They were
Yeah.
just fundamentally limited by how they ingested the world.
Well, today on this deep dive, we are going to completely shatter that straw. We're taking your entire stack of foundation model course materials covering lectures 1 through stunks, and we're synthesizing it.
Right, to help you absolutely crush your upcoming midterm.
Exactly. Our mission today is to help you ace this. We aren't just going to sit here and memorize vocabulary words because, let's be honest, that is not how you ace a complex exam.
No, definitely not.
Yeah.
You need the context.
Right. We're going to build a solid mental framework. If you understand the evolutionary narrative, how we went from looking through that tiny straw to taking in the entire museum at once, these concepts are just going to stick naturally.
Yeah, and to appreciate the power of modern foundation models, we really first have to examine the constraints of the systems that came before them.
Right, the older stuff.
Yeah, so let's step back into the pre-2018 landscape, which was the era of specialized deep learning. Back then, models were, well, relatively tiny, usually operating with under 100 million parameters.
And just for context for the exam, parameters are basically the internal variables, right? Like the mathematical weights the model adjusts and learns during its training phase.
Exactly. And they were trained on maybe 10,000 to a million tokens, but the real defining characteristic of that era was just how narrow the models were. I mean, they were built for one highly specialized task.
So if you spent months building and training a model to, say, detect spam emails, it couldn't just suddenly summarize a news article.
Oh, not at all. Or translate a document. You'd have to build a brand new architecture from scratch, annotate a specialized data set, and just train it all over again.
Which sounds incredibly costly.
Oh, it was. Hosting all those different isolated models was just horribly inefficient. And at the architectural level, the field really relied heavily on two main structures to get anything done. That's your feed-forward neural networks, or FNNs, and recurrent neural networks, or RNNs.
Okay, let's unpack the mechanics here,
Yeah.
because this is definitely going to be on the test. Think of a feed-forward neural network, an FNN, like a brilliant trial judge who suffers from severe instantaneous amnesia.
I like that analogy.
Right. The judge can look at the case sitting on the desk right now, like classifying a single image of a cat, and rule on it perfectly. Data moves in one single direction, from input to output.
But the second that file is cleared from the desk, the judge forgets everything.
Exactly. FNNs have zero memory. They retain absolutely no information from previous inputs.
Which, that amnesia is perfectly fine for standalone tasks. But human language is not a standalone picture. Language unfolds over time.
Right. Context matters.
Exactly. The meaning of a word at the very end of a long paragraph often depends entirely on the context established in the very first sentence. That's sequential data, and an FNN simply cannot process it.
So engineers introduced the recurrent neural network, the RNN, and this architecture incorporated loops, right?
Yes, loops. It allowed information from previous steps to be fed back into the network, giving it a form of working memory so it could, theoretically handle context.
But wait, if RNNs have memory, why did they hit a wall? Like, why couldn't researchers just throw more computing power at them and make the RNNs bigger?
Well, because RNNs failed to overcome the bottleneck of sequential processing. We're back to looking through that straw. An RNN processes data strictly one step at a time, word by word.
Oh, I see.
Yeah, so if you feed an RNN a really long sequence, the mathematical representation of the first word has to be passed through the network again and again for every single subsequent word.
Wow, so by the time it reaches the end of a long paragraph...
The signal from the beginning has been mathematically diluted to the point of basically vanishing. It literally forgets the early context.
Researchers tried to patch this leaking memory, though. The evolution from basic RNNs brought us gated recurrent units, or GRUs.
Right, GRUs. They were an attempt to optimize older, much clunkier models like long short-term memory networks, LSTMs.
Yeah, GRUs simplified the architecture, right? By using a single hidden state and just two mathematical gates, a reset gate and an update gate.
Exactly. And the mechanics of those gates are crucial to understand. The reset gate essentially acts as a filter, calculating exactly how much past information the model should just drop or forget.
So it sheds irrelevant data to keep the memory stream clean.
Yes, while the update gate decides what new information is actually worth keeping. And because GRUs have fewer weights than LSTMs, they're faster to train and highly efficient on smaller data sets.
But they were still just a patch, right? Like, GRUs didn't solve the fundamental disease, they just treated the symptoms.
That's a great way to put it. They were still trapped in sequential processing, reading word by word.
And failing to remember long paragraphs wasn't just like an annoyance. It was an existential threat to the progression of AI. To solve it, researchers had to entirely abandon the concept of reading left to right.
Right. That sequential bottleneck directly forced the most critical breakthrough in modern AI history. In 2017, a team at Google published a paper with a highly confident title, Attention is All You Need.
Oh, here's where it gets really interesting. They introduced the transformer architecture, and it just completely dismantled the old paradigm.
It really did. Transformers threw out sequential processing entirely. Instead of reading a sentence word by word, the model processes entire sequences in parallel.
So it effectively sees the entire input at once.
Exactly. Within what is called its context window.
And the context window is it's the strict limit on how many tokens the model can process simultaneously, right? Say like a 4,000 token limit.
Yep. And because the transformer ingests everything at the exact same time, it doesn't suffer from that RNN dilution problem we talked about. The first word and the 4,000th word are processed with the exact same clarity.
That's wild. And I'm guessing parallel execution meant these models could finally utilize modern GPU hardware properly.
Oh, absolutely. It made them vastly faster to train.
Now, for your midterm, taking a black box approach to the transformer is key. You don't necessarily need to derive the hardcore calculus on the whiteboard.
Please don't try to do that during the exam.
Yeah, save yourself the headache. But you absolutely must understand what the internal components do and, more importantly, how they achieve it. The engine powering this whole revolution is self-attention.
Yes, self-attention is the mathematical mechanism that allows each token in a sequence to calculate its relationship with every other token in that same sequence.
So it evaluates the entire sentence simultaneously to figure out what is contextually important.
Exactly. And it achieves this using three specific vectors for every word: the query, the key, and the value, often abbreviated as Q, K, and V.
Okay, let me synthesize how this actually runs the math just to make sure it's clear.
Go on,
Let's say
come
we
on.
have the word bank in a sentence. Bank could mean a financial institution or it could mean the side of a river. Right.
Right, classic ambiguous word.
So the query is the word bank, actively asking the rest of the sentence, hey, what context is around me?
Yep, and the keys are the labels attached to all the other words in the sentence.
So the model calculates a mathematical similarity score. I think it's a dot product between the query for bank and the keys of the other words.
You got it. And if the word bank finds a high mathematical match with the key for the word river sitting a few words away, the attention score spikes.
Okay, makes sense.
The model then multiplies that high score by the value, which is the actual underlying semantic meaning, pulling that river context forward.
So the word bank now confidently understands it's a geographical feature, not a place to deposit checks.
Exactly. And it doesn't just do this once either. The architecture uses multi-head attention. It runs this entire QKV attention mechanism multiple times in parallel across different heads.
So one head might be calculating the grammatical structure, another head is looking at the emotional tone, another is tracking pronouns.
Exactly. They're all looking for different types of relationships simultaneously.
But wait, this raises a massive logistical question. If the transformer processes all the words at the exact same time in a giant parallel batch, how does it know the order of the sentence?
Yeah.
Because, the dog bit the man means something very fundamentally different than the man bit the dog.
It does, and that is where the genius of positional encoding comes in. Since there is no left-to-right sequential reading, the model literally injects mathematical timestamps into the token's embedding before it ever reaches the attention layers.
Oh, wow. So it modifies the data of the word itself to include its exact coordinate in the sentence.
Exactly. So the model processes everything at once, but it can perfectly reconstruct the order based on those embedded coordinates.
That is brilliant. Okay, so the overarching architecture housing all of this is generally split into two halves, right? An encoder and a decoder.
Right. The encoder takes the raw input and uses self-attention to create a dense, rich mathematical representation of the data.
And then the decoder takes that representation and generates the final output sequence.
Exactly. And when you look under the hood of those decoders, there are specific mechanisms making the generation possible. The first one you need to know is masked self-attention.
Okay, this operates during the training phase, right? Because the decoder is trying to learn how to predict the next word. But if it can process the entire sequence at once, it would just see the answer.
Exactly. It would just cheat.
Yeah.
So masked self-attention artificially blinds the model to future tokens. It forces the model to guess the next word using only the past
That
context.
makes total sense.
Yeah. And once it makes that prediction, we hit the cross-attention layer. This is where the magic of translation happens, for example.
How so?
Well, in cross-attention, the decoder actively attends to the output of the encoder. If you're translating from French to English, the English decoder uses cross-attention to look back at the French encoder's mathematical context to figure out things like noun-adjective placement.
Ah, so it seamlessly bridges the input and the output. And woven throughout all of this are residual connections. In deep neural networks, signals can get lost as they pass through dozens of mathematical layers, right?
Right, the vanishing gradient problem.
Yeah, so residual connections literally take the original input signal and bypass a layer, adding it back into the stream further down the line. It ensures the original context survives the deep processing.
Spot on. We also have the feed-forward network, or FFN, sitting inside these layers. While attention figures out the relationships between words, the FFN applies identical transformations across all positions to add nonlinear depth and complexity to the representations.
Okay, got it.
And finally, at the very end of the decoder, you reach the generator, often called the prediction head. This is a linear layer followed by a softmax function.
And that takes all those massive abstract mathematical representations and converts them back into actual probabilities for the vocabulary. It decides with mathematical certainty what the next token should be. So we have this incredibly fast parallel processing engine. But in the real world, what happens when we feed actual human language into it? Let's transition from the architecture to the applications, like natural language processing or NLP.
Yeah, NLP bridges human communication and machine understanding. And NLP tasks test a model's genuine semantic comprehension.
Like sentiment analysis.
Right, where the model classifies the emotional inclination of a text block as, positive, negative, or neutral.
Then you have named entity recognition, or NER, which isn't just word spotting, right? It's pulling out specific categorized entities from unstructured text.
Exactly. It parses a messy news article and perfectly categorizes Michelle Obama as a person, Chicago as a location, and Harvard as an organization.
And of course, machine translation, converting text between languages while preserving the deep contextual meaning.
But the true test of these architectures lies in natural language inference, or NLI. This moves beyond simple pattern matching into actual logical reasoning.
Wait, how does it test logic?
Well, in NLI, the model is given a premise and a hypothesis, and it must determine if the hypothesis logically follows from the premise. It requires the AI to actually evaluate logical truth.
Oh, wow. And all of these capabilities ultimately combine to power text generation, creating coherent, contextually accurate human language over long stretches.
Yep, exactly.
Now, it's easy to visualize how sequence-to-sequence attention works for text. Words map cleanly to tokens. But how do we apply this to images? Like, what does computer vision look like in the Transformer era?
Well, computer vision, or CV tasks, are heavily categorized by their required level of spatial precision. The most basic application is image classification. You feed the model a picture, and it simply outputs a global label, like cat.
But classification just tells me a cat exists somewhere in the frame. If I'm building a self-driving car, just knowing a pedestrian is somewhere in the image is entirely useless. I need to know exactly where they are.
Right.
I assume this is where object detection comes in. That is the exact progression. Object detection identifies the entities and locates them using bounding boxes. It draws a defined box around the pedestrian and another box around the stop sign.
Okay, but what if you need even more granular precision?
Then you move to image segmentation. Segmentation discards the rigid boxes and identifies the objects at the exact pixel level. It traces the exact outline of the pedestrian, separating them entirely from the background street pixels.
That's incredible. And we're also seeing tasks that blend NLP and CV, right? Like visual question answering.
Yes, where you can feed an image into a model and ask it a natural language question, like what color is the car parked next to the fire hydrant?
Or image captioning, where the model generates a highly descriptive paragraph explaining the visual scene.
And the reason we can blend these worlds so seamlessly now is due to the Vision Transformer, or VIT. The VIT proved that the transformer architecture wasn't strictly limited to language.
The mechanics of the vision transformer are brilliant. It treats images just like sentences, right?
Basically, yeah.
It takes a high-resolution image, chops it up into a grid of little square patches, and treats each of those visual patches exactly the same way a large language model treats a text token.
Exactly. It uses self-attention to calculate how the pixels in the top left patch relate to the pixels in the bottom right patch. It is the ultimate expression of multimodality. We are processing text, images, and even audio using the exact same unified parallel architecture.
Incredible. As a quick practical note for your exam preparation, though, when evaluating how well these models perform beyond just chatting or labeling images, keep the human evil benchmark in mind.
Oh, definitely no human evil.
It's a specific, rigorous data set of 164 handwritten coding problems. It's used to evaluate if models can actually generate functionally correct, executable software code, not just natural language.
It's a vital benchmark. So, okay, we've established the transformer architecture and we explored the NLP and CV applications. Now we reach the final stage of our evolutionary timeline.
a big one.
Yes. What happens when we take this parallel processing engine and crank the parameter size and training data up to astronomical levels?
We enter the era of massive scale, but there was a crucial stepping stone first, right? Between 2018 and 2021, the field operated in the transfer deep learning era. Models like BERT defined this period.
Yes, transfer learning fundamentally changed how we build AI. Instead of starting from scratch for every task, you build a large base model, say 100 million to 1 billion parameters, and you pre-train it on a massive corpus of text, perhaps up to 10 billion tokens.
But during this pre-training phase, you aren't teaching it to do a specific job like sentiment analysis or translation, are you?
No, not at all. You're just forcing it to read over and over so it learns the general mathematical structure and grammar of human language.
Then the transfer occurs. You take that massive, generalized mathematical understanding, you bolt on a specialized prediction module to the top of it, and you fine-tune the model using a much smaller specific data set.
Exactly. You transfer its deep knowledge of English into the specific job of, say, identifying spam.
So you still end up with a specialized model, but you saved millions of dollars in compute because you didn't have to teach it how to read from scratch.
Right. It was hugely efficient.
But post-2021, the industry crossed a threshold into the true foundation model era. And the sheer scale here is, well, it's almost difficult to wrap your head around.
The jump in magnitude is staggering.
Yeah.
We scaled from 1 billion parameters to models containing anywhere from 7 billion to over 1 trillion parameters.
Trillions. Unbelievable.
Yeah. And the training data exploded from 10 billion tokens to between 100 billion and 30 trillion tokens.
Yeah.
They are ingesting essentially the entirety of the digitized human record.
And at this massive scale, the entire engineering paradigm shifts again. We stop bolting on specialized architectures, we train a single monolithic model once, and then we simply prompt it in natural language to do whatever we want.
And the reason this works is perhaps the most fascinating concept in modern AI emergent abilities.
Right.
When researchers scaled these models up, typically crossing the threshold of about 175 billion parameters, the models suddenly began demonstrating behaviors they were never explicitly trained to do.
This is the real aha moment. These models were only ever trained to predict the next word in a sequence. They are, at their core, sophisticated autocomplete engines.
Exactly.
But by forcing the model to accurately predict the next word across trillions of pages of human knowledge, the AI actually had to build an internal mathematical model of human logic, reasoning, and physics just to make accurate predictions.
Which leads to incredible generalization. They develop high proficiency in few-shot learning, where you can give the model just 2 examples of a complex logic puzzle in the prompt, and it instantly figures out the underlying pattern to solve a third.
Or zero-shot prediction, where it perfectly executes a task it has never seen before without any fine-tuning or examples at all.
Yes. The self-attention mechanisms, operating across trillions of parameters, map concepts so deeply that reasoning becomes an inherent emergent feature of the network.
Let's bring this all together for your midterm preparation. Remember the evolutionary arc. We started with feed-forward neural networks that suffered from complete amnesia.
Right.
We progressed to recurrent neural networks that had memory but choked on sequential processing, diluting context over time.
But then the 2017 Transformer revolution shattered that bottleneck. It introduced parallel processing, massive context windows, and self-attention, allowing models to process all the relationships in the data simultaneously without losing the big picture.
We applied this powerful architecture to NLP tasks like named entity recognition and natural language inference, and CV tasks like object detection and segmentation, eventually unifying them with vision transformers.
And finally, by scaling this architecture up through transfer learning with models like BERT and exploding the data to trillion-parameter scales, we arrived at the multimodal foundation models of today, defined by their zero-shot emergent abilities.
It is a stunning technological trajectory. But before you head into your exam, consider this final provocative thought. Right now, these massive foundation models are almost magically good at token generation. Predicting the next word or the next image patch based on the statistical patterns they absorb during training.
But generating the statistically most likely next word is not the same thing as possessing a true world model.
Exactly.
The frontier of AI research is currently grappling with the limitations of autocomplete. If a model only predicts patterns, it isn't truly reasoning or planning.
The fundamental question is, how will AI architecture need to evolve again to move from simply predicting the next token to actively planning, self-correcting, and actually understanding the physical laws of the real world?
Yeah, it makes you wonder what the next attention is all you need breakthrough will look like.
It really does. Well, good luck on the foundation model's midterm. Just remember to put down the straw and take in the whole picture.